to compute our numbers. We're going to compute our numbers to determine the outliers. Right now, it's important to realize, as a guide, we're using 3 standard deviations here. If your sample is really small, you may consider 2 standard deviations. If your sample's gigantic, you may consider 4. That's a little doubtful, but right. And now we're gonna use 3, and then we're gonna figure out what 3 standard deviations is, and then subtract that from the mean score to identify our outliers as so. So our standard deviation was 1.94. Right? So 3 times 1.94 is 5.82. Okay, so that's 3 standard deviations, right? 3 times 1.94. So then we add and subtract that number from our mean. So if we take our mean of 43.25 and add 5.82, we get 49.07. So therefore, any scores above 49.07 are above 3 standard deviations, right? And our outliers are high outliers. Now to get our low outliers, we do the next line, where we take our mean of 43.25 and minus 5.82, right? Minus instead of add, which is 37.43. So that's our low outlier. So scores below 37.43 are outliers on the low side, extremely low scores. Now we have our extremely high scores and our extremely low scores. So if we looked at our frequency table, right, we could even draw little lines, right, saying these are the frequencies, right? The one person that was making 37,000, the 37.0, right? Their score is below 37.43, so they're an extremely low score, right? So they're an outlier extremely low. Then the 52.0 at the bottom, that's one person. They're above the cutoff rate range of 49.07, so they're an extremely high outlier. So we have our extremely low and our extremely high scores. So that's one method of computing them or identifying the outliers. Next, we can look at the stem and leaf plot produced by SPSS in identifying our outlier scores. So again, as always, we have our path, right? So analyze descriptive statistics, but this time we select explore and we enter income in the column, and then under plots we check stem and leaf, then continue and OK, and what we get is something like this. And so the one, the way up high, right? You can see on the left-hand side, on the axis, right, on the vertical axis, that's the between 50 and 55, right? So that's our 52, our score of 52. And then between 35 and 40, we have another circle with a 2. Right? So that's the second outlier, and that's our extremely low score, the 37. Right? So if we want to label everything, we could look at it like this. Right? So the box, right, it has a median value, and then the little handles have the range, and then we could see, right, the scores outside that range. So that's one way of identifying it. So the thing to do, right, after identifying those outliers, the thing to do is get rid of them, perhaps only temporarily. So you could do this in many ways. See page 107 of the textbook, the Steps of Data Analysis textbook, to look at how to recode, right? So you could recode income into another variable where it excludes those high and low scores. So it's the same exact variable without the outliers, right? Then you would retest that variable without the outliers for normality. Now, what's very important to realize is, and I'm going to say this a couple of times, is the problem isn't the outliers per se, it's the undue influence of the outliers. So you'll hear this again, but if you're doing linear regression and you think the outliers are a problem, you should test for them either way, whether you think it or not. And so after you test for them, do the linear regression with the variable without the outliers, and then repeat the linear regression, with the untransformed variables with the outliers included. Right? So basically, you want to see if the results change in terms of, say, statistical significance and so on when the outliers are included or excluded. But if there's no significant difference, like if the findings are the same regarding statistical significance, then you could use the untransformed version, with the outliers, and state that the test is acting robust, right? So even though there's outliers, the test is robust, and they're not having an undue influence on the findings. Again, that's right at around page 107 in the book. All that's repeated. So then we retest after the outliers are removed. So this is our transformed variable for income, right? The one where the outliers are not included. Now you can see the Kolmogorov-Smirnov and Shapiro-Wilk, they're both still saying that it's significantly non-normal, the distributions. So that didn't really help solve that problem as per that test. However, if you look at the skewness and kurtosis relative to the ratio of the skewness and kurtosis, you could see that it did help solve that problem. So the skewness, right, the ratio is even lower. So instead of 2.36, it's actually 0.07. So the skew is almost right in the center, according to those numbers. And the kurtosis, right, the ratio now is, the kurtosis is negative 1.39. The standard error is 0.483. And if you divide negative 1.39 by 0.483, you get 2.88. So the ratio of the kurtosis relative to the standard error of the kurtosis is right around 2.3, right? So it's approximately normal. So that removing those outliers did make the distribution approximately normal in terms of kurtosis, and even more so too for skewness, right? So that's one way of solving that challenge. Now 3, data transformations. Now here we have to have the old grain of salt, okay? Because there's pros and cons when you use data transformations. So what it does is it mathematically reconfigures your distribution to be more normal. Say it multiplies every value by a certain number and all the values by the same number to redistribute them. The most commonly used is the log odds data transformation, where it pushes the cases to the right. So if everyone's bunched up on the left in the bell curve, it spreads everyone out toward the right, making it more normal, right? Now it's important to note, it sounds real good so far, but it complicates the interpretation of the actual statistical parameters of the numbers. In other words, if you, and you'll hear this again too, if you do a data transformation, the mean, per se, changes. And it's no longer the mean within your sample, right? It's a mathematically reconfigured mean, right? So it's not meaningful. And that's a very, very important point, right? So in order to do the log odds transformation, you go to transform and compute variable. And then, like I said, this is in the text a little more expounded. So under function group, take arithmetic, and under the functions, you take LG10, which means log odds 10. You put her up there, and then you put it in the upper left-hand corner of the dialog box. And then you enter the variable that you're going to take the log odds number for, right? So income. So we put income in there to take the log odds of income. Now, an important note, if you try this, sometimes you get kooky numbers, and one of the first things to check for is is there a 0 in your distribution, right? For example, income. Are there like 100 people that reported 0 income, right? Because when you do the log odds, if there's a 0, the log odds can't handle it. Right? All the numbers have to be 1 and up. Right? So that's the little asterisk down there. If it's less than 1, if it's 0, you got to change it. So if you have zeros in your distribution, you have to use the data transformation and add 1 to all values. So all values stay the same relative to each other because you're adding 1 to all of them. And then if you add 1 to the zeros become 1, and the 1s become 2, and the 2s become 3s. And that's what you need to do if you do a data transformation with zeros in your distribution. That's not so much, it's not so important to worry about now. It's just if you ever get to that point and you do a data transformation and it doesn't work out, you'll be happy to know that that's a possibility. All right, so here's what I was pointing out before. So we have our mean. Now our mean, right, instead of 43, is 54.31. Now we didn't add more people to the sample, right? So that mean is different for another reason, besides that the number is actually changed according to the sample. As I said, the mean has changed because of the data transformation. So now you can't use that mean to say, this was the average income within my sample, right? Because it's not, as we saw before. So important thing to realize is you gain something and you lose something. So you may gain a more normally distributed variable when you do the log odds, but then you lose the detail within those numbers that describe your actual sample. Right? It's important to realize that, because not everyone does. So then after you take that log odds, you put it back into the frequencies, you get your skewness and kurtosis and all that. Right? You may even repeat our more stringent tests here, which of course are still saying, right? So I told you these are strict, these tests, right? So I'm telling you, they're strict. So they're still saying, even after the data transformation, even after taking out the outliers, right, that the sample is significantly non-normally distributed, right? And like I said, that's largely a product of a smaller size sample, because the tests are sensitive to smaller size samples. Right. So you can see, even by our second criteria, the standard error relative to the skewness and kurtosis, is still saying that the kurtosis is significantly non-normal. Okay, so sometimes, you know, the data transformations help. In this instant, they weren't as effective as removing the actual outlier scores. So you got to play around with that, and you have to see what's most effective, and then report it in your methods. So, as I said, you can repeat the tests with the transformed versions of the variables, be it log odds or removing the outliers, right? And then repeat it with the original form of the variable. So the original income versus the one without the outliers versus the transformed income. And if there's no significant differences, as in like, you know, the same statistically significant relationships exist, I would recommend using the original untransformed version and then just report in the methods, you know, that there were some outliers, you know, but it didn't affect the levels of significance for testing. That's a good way to go about it. We could state, analysis indicated the variable income evidenced a non-normal distribution. Then we could say, analysis was repeated using a transformed version with a normal distribution, and findings did not differ in terms of statistical significance. This is what I'm saying. Then they know what we did. Right? And then if they agree with what we did, they could consider the findings credible. And if they disagree, they can, you know, think otherwise. But at At least they have that option. Now, multicollinearity, right? I don't know why these words are so long, but they are. So multicollinearity are when two continuous predictors in a multiple regression model are highly correlated. And now the findings are distorted when there's a certain level of correlation. So at a certain level of multicollinearity, the findings are distorted. Very important point. So if we're looking, say this is our model. We want to know how age and income impact happiness, right? So as you get older, do you get happier? As your income goes up, do you get happier? This is what we want to know, right? But suppose it's not that simple, right? So suppose, in addition to looking at those direct effects, there's a little relationship going on between age and income. So as you get older, you make more money. So there's a correlation. So as age goes up, 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 income level also goes up, 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 right? So it's a very high correlation. So this may be what happens in our analysis. So individually, age may significantly predict higher levels of happiness. That might be a true finding, right? Also, income might have a true finding where higher income predicts a higher level of happiness. So as income goes up, happiness goes up, right? So it's all fine so far. However, when you put them together in the regression model, because it's one test where age and income are together predicting happiness, right? In the regression model, age and income might not get along. What happened is the high correlation between the two causes multicollinearity, and what happens is the results indicate neither is significantly related to happiness, when in actuality both are. So the multicollinearity actually hides the significant relationships being tested for. Right? So if we saw this model and we didn't know anything about multicollinearity, we might say, oh, age and income don't impact happiness. But if we did know about multicollinearity and we realized they could be correlated, we might say, if those two are correlated, they could be hiding those relationships. Right? So we have to test for it and see if that's what's going on. So again, SPSS has a simple function, right, to tell. So we could look at tolerance, right, which should not be below 0.20. If it's below 0.10, it's real bad news. It's a major concern. And the inverse of the tolerance is the VIF, the variance inflation factor. And that shouldn't be above 2.5 or 3.0. Mostly it should be around 1 for each predictor, right? So these are simple indicators looking at our multicollinearity. So you have the old path in SPSS. It's actually a function within the linear regression model. So if you go to Analyze Regression Linear and put in happiness in the DV and income and age in the IVs, then you go under Statistics in the dialog box, click Collinearity Statistics, then Continue, and then OK, or Paste. The output will produce tolerance VIF values for the predictors. It's that simple. You just know how to do it. You just have to know to do it and how to do it. So here we go. We have our tolerance and VIF in the output. So please note, under the collinearity statistics, the tolerance is way above 0.20, right? So it's 0.916 for income, 0.883 for age, and then education, 0.928, and the VIFs are all around 1. So that makes it appear to us that there's not a problematic level of multicollinearity within our regression model, right? So this is how we tell if we have true findings or findings based on, the violation of test assumptions. So we're looking okay for multicollinearity. Now linearity, right? So you could imagine if we're using multiple linear regression, that's the most appropriate when you have linear relationships. Right? So a linear relationship exists between continuous variables. In our case, we want to examine a relationship such as if income is continuous and it's a predictor of happiness, which is continuous, do they have a linear relationship, making it appropriate for linear regression? Okay. So in these three figures, we have all sorts of linearity patterns. Okay? The first one is what we might expect when we look at happiness and income. For example, if the x-axis on each of these figures is happiness, happiness goes from 1, 2, 3, 4, 5 as measured on our scale. And then imagine the y-axis is income. So the first one is a positive relationship as happiness goes from 1, 2, 3, 4, 5 going up. The y-axis, income, also goes from 1, 2, 3, 4, 5. You can see the intersecting, right? One intersects with 1. So if you're making, say, that's 100,000, the 1 on the y-axis, you have a happiness level of 1. But then if you have 2 intersects with 2. So if you have an income of 200,000, you have a happiness level of 2. Then 3 intersects with 3, right? So if you have 300,000, you have a happiness of 3. 4 intersects with 4, and 5 intersects with 5. So the highest level of happiness, 5, intersects with the highest level of income. Say that's 5 for 500,000. Right, so that's a positive linear relationship. You could also have a negative linear relationship, which is in the second diagram, where, right, as happiness goes up, the income goes down, right? So that's a negative relationship, and that's okay too. It's still a linear relationship. The last one, that's the problematic one, right? That is the curvilinear relationship. That's where it starts off being positive, and then at a certain point, it turns negative. So it starts going up, up, up together, then it starts going down, down, down. Right? So it's a curvilinear relationship. So curvilinear is not linear. So if that was the actual pattern, it would not be appropriate to use linear regression because the relationship is not linear. Right? So that's one of your checks. And we'll talk about measuring that in a moment. But first, let's talk about homoscedasticity. Right? So homoscedasticity is an equivalence of variance, right? So it's equal variance of the independent variable at different levels of the dependent variable. And that's expounded upon a bit more in the book, right? So we just want to touch on it here. But for further reading, we can see the textbook. So to look at linearity and homoscedasticity, we would follow this path in SPSS, again, in the linear regression function. So again, we enter our DV happiness and our independent variables income and age, but this time in the dialog box, we go under plots and we click Z resid and by Z pred. In the X and Y boxes, then continue and OK or paste. And we'll get a scatter plot, right? So if we have good homoscedasticity and good linearity, you'll see a random dispersion of dots around the 0. So this is where our term equivalence of variances comes in, right? So everything seems to be varying equally. The residuals are just evenly dispersed equally all over the place, right? What's problematic is if we get a pattern such as this funnel shape, right, where it's small on the left and it becomes big on the right, right? So that's poor homoscedasticity, which is heteroscedasticity, right, where the residuals are kind of biased and favored toward the right, right? So it's an unequal variances, right, because they vary a lot on the right but not on the left, right? So that's a problem. by the way, to address a problem like that, you might also consider the data transformation, because sometimes the data transformation will also redistribute the residuals to be more equal in this manner too, as well as the linearity. So if linearity looks like this, that's a problem too. It's making that funny curve shape, like the curvilinear, right? It's making that funny curve shape, so that's bad linearity. Okay, so that's violating that assumption. Right? So once we've checked all those, then we want to check the undue influence of the outliers. Right? Like earlier, we looked at how the outliers were impacting the normal distribution, right? Making the distribution non-normal. But we also need to check, and this was touched upon earlier, but we also need to check if the outliers are having a significant influence on the results of the study, right? So there's just a few outliers making the relationship statistically significant. That's not a true finding. That's just based on some aberrations, some outliers, right? So again, outlier is the point that is distant from the mean, right? It's an extreme high or low. For example, if the mean score of happiness is 3.5 with a range of 1.0 to 5.0, an outlier score might be a score of 1 or a score of 5, right? It's really distant from the mean. Even one outlier, in some cases, can produce a false finding. So sometimes you'll get a statistically significant relationship between the independent and dependent variable where there is no relationship. It's just this one outlier playing havoc with the test. And if you don't know how to check for the one outlier, you might come to an erroneous conclusion. Right? So what's important to realize, too, is the outlier is not necessarily the problem. It's the undue influence the outlier has on the study findings. So you don't necessarily have to take out the outliers and leave them out. You just have to, you could take them out and see if the study findings change once they're removed. And if they do change, it could be the outlier is having an undue influence on the study results. Right? If you take it out and the results don't change, like I said, I would consider leaving the outliers in. You could note them in the methods and say they didn't have an undue influence on the findings because the findings remained statistically significant with and without the outliers in the same manner. Right. So for example, let's illustrate this. So suppose we did a t-test, an independent samples t-test to be exact. And we have two groups. We have 47 people that live with the cat and 53 people that live with the dog. And we're going to use this t-test to identify if there's a higher mean score of happiness for one group relative to the other. And you can see here that those that live with the cat have a higher mean score of 3.02 relative to those that live with the dog who have a mean happiness score of 2.48. Now below, the significance level, the two-tailed significance level is 0.000, which is below 0.05, indicating that this difference is statistically significant. So in essence, what it's saying is there's a finding where people that live with the cat have a statistically significantly higher happiness score relative to the people that live with the dog. Okay? So let's say that's the true finding. Okay? If we just threw 3 outliers into each group, 3 high scores for cat and three outliers for cat and 3 outliers for dog, right? Making each significantly higher and lower, what happens? So that's just 6 people added, but they're all outliers. Then the mean sort of remains pretty close for the cat people, right, to 2.90, but for the dog people, now it's 2.61, right? So we entered a few really low scores for the cats and a few really high scores for the dog, and it brings the means closer to one another. But more importantly, if you look at the significance level, it went from 0.000 to 0.09, which is no longer statistically significant. So what's happened here is that just those 6 outliers hid the significant relationship that was present, that we originally identified. Now that relationship is hidden by these 6 outliers. Right? So if we publish this without looking for outliers, we would publish incorrect results with incorrect conclusions. Also important to note that outlier scores can just as easily make findings look significant when they're not, relative to making findings look not significant when they are. Right? Like I said, they play havoc. So the big question is to consider in our little philosophical stint is if a researcher conducted a parametric test but did not check for the influence of outliers, how could you be sure that the results are not just errors based on outlier scores? And the truth is you cannot. So that's why this is so important. It's a bit involved, but it's really important because, like I said, what good is having a study if the findings are incorrect? And if you have to go, through these steps to make sure they're correct, it's worth it because it's not worth anything to publish a study where the findings may be dubious due to mistakes regarding data integrity. So here we go. We've completed 1, statistical power, and 2, test assumptions. And now we'll be going into 3, missing data, and then 4, measurement tools. Now, regarding missing data, it's an extensive topic. So what we're doing here is touching upon the main important points, right? So we're going to touch upon the important points, and for more elaboration, we see the book, right? But these are the important introductory concepts that really lay the foundation for missing data right here. So missing data, what is missing data? So usually it's where there's no data value, be it in the cell or on the survey. Like people complete a survey and they don't enter a selection or number. And then in the database, there's no number entered for that item, for that person, based on the survey not having a response, right? So that's missing data in general. Right? So we need to look at missing data in a few dimensions. So first, we want to know how much data are missing in a study. Is it like there's 100 questions with 2,000 people, and there's like 3 or 4 items unanswered? Or is it a sample of 100, and there's 20 items unanswered among 30 people? Both present significantly different challenges. Then 2, are there patterns to the missingness? Right, so if there's 20 items missing among 100 people, is there a pattern to the missingness? For example, are all the missing items related to, the men? So men have 20 missing items, and then the females have 0 missing items, right? That's a pattern to the missingness. It's important to know, especially in terms of generalizability, right? It's hard to generalize to the whole population if segments of the population were more likely not to complete your measure. And then the big one, how are missing data treated, which is what we'll address here, because this is the point that really challenges most people. So you have missing data, how do you account for it? That's the big question many times. All right, so as I said here, we will discuss the treating the missing data, right? Not the amounts and the patterns, although that's pretty well expounded in the text. So you have an empty cell, Right? And SPSS has a listwise deletion, so if it has an empty cell, it kicks that person right out of the analysis, right? So suppose you want to keep that person in the analysis. How do you estimate the value for that empty cell? Important to consider, some people use complete case analysis, right? So if you have 1,000 people and 800 have complete data and 200 have missing data, you just exclude the 200 and you just use the cases with complete data. There's challenges associated with that, as in there might be reason to believe the people with missing data are significantly different than the people that provided data. So you might not want to exclude them, right? But if that's not the case and you're doing complete case analysis, then you don't have to worry about the missing data. Otherwise, you have to figure out a way to enter a number in that empty cell where the data is missing, or the data are missing. So if we have income, right, and it's missing. So we need a little cautionary tale here, because I'm saying how important it is, and that's just me saying it. So I should provide some support, right, for the statement. So consider if you have missing values for income. A common way to enter a missing value is to use mean substitution. So you look at the mean value for the cases that did provide data, and you enter those for the cases that did not provide data. This is real risky, and this is probably the most common one used, but it's very risky, and I'll show you why. So suppose we have 13 study participants, and we want to look at the relationship between income and happiness, okay? So the mean income, so this is like, say this, we knew all the data, and the mean income is 50,000. So just assume that we have all this data, and this is the real, true world, values in the population. If you break it down, you'll see the first 6, right, IDs 1 through 6, the first 6 have a mean income of 50,000, but then the low income for the middle 3 is 30,000. They have happiness scores of 1. Then the high income for happiness score of 5, right? The high income of 70,000 is associated with a happiness level of 5, right? So we could see here, it looks like that low and high income are related to low and high levels of happiness. Okay, so if we break that down, what do we have? We have 6 study participants that have a mean income of 50,000 and a happiness score right around the middle of that 1.5 distribution of 3.5. We have 3 study participants that have a mean income of 30,000, and that's lower than the 50,000, and also their mean happiness scores are also lower. They're 1.0. Right? So the low income has a low happiness score. The middle income has a middle happiness score. And then the last 3 study participants have a mean income of $70,000. Right? So that's significantly higher than the mean. And their mean happiness score is also significantly higher than the mean happiness score for them. It's 5.0. So we can see a pattern here where higher income equals higher happiness scores, and lower income equals lower happiness scores, and middle income equals middle happiness scores, right? So you may have heard this before, but the most likely to be skipped item on a survey is income. People don't like talking about their income, and usually when they don't like to talk about their income, they usually have a really high income they don't want you to know about, or a really low income they don't want you to know about, right? So let's assume that those bottom 6 are missing, right? So if the high and low are more likely to be missing, high and low incomes are more likely to be missing, let's make them missing, right? So their happiness scores are still there, so we can assume they provided their happiness scores, but they didn't want to tell us about their income. So what do? So we need to put something in there for income. What do? So a lot of people would enter the mean income for the total sample, which is $50,000. So this is done commonly. So now the people with the low happiness scores are associated with 50,000. The people with the high happiness scores are associated with 50,000. And the people with the middlemost happiness scores are associated with 50,000. So by choosing that method to account for our missing data, what have we done? We've made it look like that happiness is no longer associated with income, because now it looks like everyone has the same income, right? The 6 have 50,000, the 3 have 50,000, the bottom 3 have 50,000, right? And the high, low, and middle happiness scores are all linked up with the same level of income because we chose to use the mean level of income to account for our missing data. So many times this is done in studies, and it's not even reported in the methods. So you don't even have the option of saying, oh, how did you account for those missing data? Did you use mean imputation, mean substitution? You just don't know. So it's hard to figure out how valid the findings are, because you can see it makes a big difference on the findings. Right? So due to the choice, like I said, the reality is distorted, as now happiness is equally related to low, average, and high income levels. So researcher, like I said, they may impute the means. They may even report that they did impute the means. But then you have to ask, well, did they impute 1 or 2 means, or did they impute, half the sample? That needs to be reported too, because that could have a very differential effect. So as we have in the text, right, a better choice for estimating a missing value may include using the mean of valid responses. So like on page 170, if we have our happiness scale, if we have, say, 10 items per se, and 1 item is missing, we might account for that missing item by using the mean score of the 9 items that were provided. Right? So that's one method to consider. Now, another method, so if you have missing income values, right, that wouldn't work for that. You might consider using multiple imputation, which is actually not covered in the book, but is now on SPSS and is rather simple. So what the multiple imputation does is it looks at the profile of the person, right? So all their demographics and their scores on other variables. It makes a profile of them, and then it looks at how people similar to them scored. So what was the mean income for people similar to them, and it makes several iterations, several estimates in a final one on what that missing value is. So that's considered more of the acceptable cutting-edge way to estimate missing values. So now we have gone down to number 1, 2, 3, missing data is done. We have our measurement tool to discuss, right? Measurement tools. There are 2 big topics related to measurement tools. There's the reliability and the validity of the measurement tools, right? So as an illustration, let's choose the reliability, right? There's several types of reliability estimates: inter-rater reliability, test-retest, inter-method, and internal consistency. Now, of all the tests of reliability and validity, you'll see in the literature, this test of internal consistency is the most reported. So that's what we'll focus upon today. It's the most ubiquitous measure. So if you have a study, you're reading a study, and has one report of reliability and validity, it's probably regarding the internal consistency of the study scale. So let's look at that. So basically, the internal consistency is asking, is a single construct being measured by a set of items, right? Like our happiness scale. So if we have several items, are they all combining to measure happiness? Or does some measure happiness and some don't, right? So that's what we're examining. If a single construct like happiness is being measured, the items will be correlated in a pattern. And the pattern will look like this, right? So say this is our happiness scale. And somebody is very happy. They have high levels of happiness, right? So are they happy? One, they're going to say strongly agree. I felt happy in the last 7 days. Have you felt sad? One, right? It's hard to feel sad and happy at the same time. And then the remaining positive items, good, strong, glad, all tend to be on the higher end where the happiness is. So that's a pattern indicating high levels of happiness. Right? And here's a pattern indicating low levels of happiness, where happy and the other positive items are one, but sad is strongly agree, right? So that's correlated to be low levels of happiness. And then this one that really doesn't have a pattern. And so this is not showing much. It's not correlated. Because a person says, have you felt happy in the last 7 days? I said 5. Strongly, have you felt sad? Strongly agree, 5. Right? So unless they're catching some like really emotional movies or something like that, you know, it's really not, it doesn't seem like a reliable measure of happiness, which we're trying to ascertain. So the intercorrelations, right, the correlations reflect the presence or lack of presence of internal consistency. So the internal consistency is most often reflected in the Cronbach's alpha. And so that's a test we could do in SPSS. It ranges from 0 to 1, right, 1 being the highest, and a score of 0.70 or above is considered reliable. Well, that is sort of low, so 0.80 or 0.90 is even better. All right, so here's our path in SPSS, Analyze Scale Reliability Analysis. So you take all the items on the scale from the left-hand column, put them in the right-hand column. Remember to go to Statistics and click Scale if Item Deleted. That will tell you if you have a scale below 0.70. Right? I'm going to say this again. Right? So it's the mother of teaching, repetition. That'll tell you which to remove to increase the scale reliability. Right? And then continue or OK and paste. Right? So again, if the Cronbach's alpha is less than 0.70, so it's not considered reliable, check that scale if item deleted function. See if there's like one item, because it'll say one item removed will bring the scale to like 0.7 or even 0.8 sometimes. And the other thing to check is, are there any reversals, right? Like on page 79 of our textbook, we did that in the first presentation. Like the sad item has to be reversed, right, for that scale. And if you forget to reverse it and put all the items together in reliability analysis, you might get a low reliability because that item wasn't reversed and you have the original version in. So there you have it, our checks of data integrity. All 4 are done. And just to sound like a completely broken record in summation, these are entirely necessary for a credible study. Findings can easily be spurious, and the quality and future of statistical research hinges on making these appropriate checks. Next week, we will be going to steps 4 and 5, univariate and bivariate analysis, and I look forward to seeing you there. Okay. Thank you for watching, and have a great day.